Mark is also arguably the world's most prominent, shall I say, materials celebrity. He is a frequent contributor to the popular press. He writes for The Observer, for The Times, for The Wall Street Journal, for The Guardian. He regularly gives popular talks on engineering and material science to TV, radio, festival, school audiences. He gave the 2010 Royal Institution Christmas lectures, and he's a regular presenter of science and engineering on BBC television. In 2014, he was elected a Fellow of the Royal Academy of Engineering. In 2016, he was awarded the American Association for the Advancement of Science Prize for Public Engagement with Science. And not least, he also wrote the New York Times best-selling book about our field, Stuff Matters, which is pictured here, and which is also the title of today's John Wolfe lecture. It is truly a delight that we finally have Professor Mark Miodownik here with us at MIT and in DMSE, and I'm excited to introduce him and his talk to you, Stuff Matters. Mark?
Yeah, I think that's on, actually. So, thank you very much for that very kind, generous introduction, which is going to be very hard to live up to, but I shall try. That's quite a hard, yeah. Anyway, thank you. And it's such a delight to be invited to a place that is kind of, one of the epicenters of material science in the world, has been for, more than a century. And so, yeah, it's great to be here. And I want to sort of share with you, why it's such a great subject, really, and why I love it so much, and by sharing it with you, hopefully provoke you into thinking about the future of material science, the future of our world, because those two things are inextricably linked, in my view. But to do that, I feel I need to just go back in time, tell you why I ended up being a material scientist, and also, where materials come from. So this is a very kind of a humble picture from outside my lab in London a few years ago, and it's where I used to catch the bus home. And buses being very infrequent in London, I used to just sort of amuse myself by counting the materials I could see until the bus came. And this public transport system in London and the UK is terrible, and so it doesn't often. This is just a fraction of those I'd have to count to get there, get home. But it always really amazed me that it's just even in such a mundane, everyday environment, how many materials there are. And this is true here, right? And once you get good at picking them out and seeing them, it's sort of impossible to stop. It's a sort of addiction. And then you ask yourself, well, yeah, it is. Sorry about that if I infect you. And then once you think about that, you think, well, each one of those materials, where did they come from? Who invented it? Why do we still have it? They cost a lot of money to make and produce, and then they end up everywhere. And then you think about it, well, actually, each one of these materials is a revolution in its own time. Each one changed us. It kind of took us forward. And this is, of course, why the ages of civilization are named after materials. If you ask anyone that, they say, well, there's always the Stone Age. And if you get stuck in the Stone Age, that's it. You're naked and cold, especially in places like this, and muddy. And it's not much fun. And so in order to sort of get through that, to make tools, we had to work out how to turn stone into metal. And that was a massive thing. And that required a good deal of thinking and technology. And then the tools came along, we could make stuff, and we could make clothes and architecture. And you have the pyramids and these incredible structures. And then the power that we kind of understood, that what you could create meant that we could create all these other materials. And each one of them is a solution to a human problem, right? So if you're looking at that, you're looking at a mirror of who we are. These are our problems that we've solved, or not just problems, actually. In the end, we got so good at it that we started to kind of try to achieve our dreams. So dreams of flight, of going to the moon. All of these required new materials to be created. And of course, if you take them away, we are just naked, and we aren't who we are. So these are meaningful things. This is where we come from. And it's not true to say that these are all the products of science. These are the products of culture, actually. This is what culture does. Human culture creates new materials, and it creates them in the form of art and architect. It creates cinema. I mean, the celluloid revolution, that is plastic. The onset of plastic into our world was cinema. These two things are the same thing. Visual culture was changed at the same time that materials changed. It allowed it. Photography, again. You see this with the mobile phone. And the mobile phone and internet culture is a materials innovation. So this is a cultural stuff. So where does material science come in? What bit of this is material science? How do you understand the science of this? And of course, the last 100 years have been this acceleration of the discipline, and it's just got more and more exciting. And it's very hard to kind of conceptualize all of that in one slide, but I'm going to do it. And here it is. This is, in a way, kind of a map of the world, of that world I showed you before by the bus stop, but now it's a different way of looking at the world. And this is the material science way of looking at that world. And it's about scale. It's about scale and structure. And this is how to understand how to make new materials and how to control them. And it's basically big stuff at the top, smaller, 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 smaller. And it's split into two sides. You have the living side over here. So this is animate matter. And you have the man-made world over here. And let me just sort of spend a few minutes going through this map, because I think this map is as important as that map of the globe. The first astronauts showed us what the Earth looked like from space. And that was a culture-defining moment. It changed the consciousness of humans. And this is the same thing for material science. This changes everything. And I'll just take you through it. So you have big stuff like big trees and whales and mice and fleas on the mice and hairs on the fleas. And if you zoom into the hairs, you find that these are made of many different cell types. And in fact, tissues, your skin, your teeth, your liver, your kidney, your brain, these are all different tissue types, and they're made of different cell types. And they are matter, they are stuff. But your skin is a sort of plastic stuff, an incredible plastic stuff at that. And your teeth are sort of ceramic. And yet, they all start from the same thing. They all start from a single cell. So you started a single cell, a flower, a bird, all start from a single cell. And that's an incredible thing to think about. So a cell, a squidgy bit of gel, can turn into something as hard as a tooth, as flexible as your tongue, as thinking clever as your brain, by jumping from this to this. And if you try and work out how one cell can do that, it can be both hard and soft, then we look inside the cells and we find that they're machines, actually. Cells are machines, and they're kind of factory of different operations. And I don't mean that, obviously, in a kind of metaphorical way. I mean, the more we find out, the more we realize that these machines open up holes and let things through, and they build scaffolding. And no one tells those machines what to do. It's a self-organizing system. They have energy in there, and they have information that codes for those machines. That's called DNA. So when you take, essentially, living matter apart, this is what you find. You find that it's a nested set of structures, and that you are a multi-scale being. And the properties of your arms, your muscles, your ability to walk, your ability to think, your consciousness, they are all somehow in there, right? But they are not at any one scale. They are an emergent property of those scales. So here's the paradigm that material science gives you, which is that you cannot explain you or any other living creature by just looking at any one scale. You have to understand all the different scales and how they fit together, and crucially, how they influence each other. So it turns out that if you were to ask someone, what is life? What does living mean? What is it to be alive? People have many answers to that. A sunny day. I love breathing the air. People have answers. But what makes the difference between a living matter and a non-living matter on this side? No one can really explain it. I mean, it's a big, outstanding question. Probably a Nobel Prize in this century will go to someone who can really put their finger on what it is. But it has to be something to do with the way these scales are connected, right? It has to be, in my view. And one thing that we know is that information breathes up the scales. So information goes from this scale to this scale to this scale to this scale and up. So it's not that you magically get cancer, and it's not that you magically think a thought. It's that actually, through the different scales of molecular structure to cellular structure to tissue structure to macrostructure, information is traveling. And back again the other way too. So information travels from the macro scale down into your genes and turns different genes on. We know this. So this is a living, breathing material structure, constantly changing each structural scale, adjusting it, repairing it. And that's some sketch of what life, animate matter is, okay? So what then of the inanimate world, the world that I was so proud of at the bus stop? Well, it seems less impressive now, right? Because the animate world has managed to create, fish that can swim and birds that can fly and people that can fall in love from the same stuff, a few atoms, we haven't quite done so well yet. But that's why material science is so fascinating, because you look at this side and okay, well, we can do it then. There's a whole panoply of what's possible out there. But even if you look at what we've achieved so far, it's still quite impressive. We could obviously make big rockets that go, hopefully, to Mars at once, robots, phones. If you zoom into those, you get tiny little wires. That seems trivial now, but that was an amazing achievement. Watches, little micro MEMS machines, which have feature sizes smaller than the hair of a flea. This is easy now. These are inside your phones. These are inside your cars. They're little mechanical devices that know which way gravity is by intercalating and changing the capacitance. And they initiate your airbag in a crash in a fraction of a second before you even know you're in a crash. And there it is, a tiny little machine. But it's easy. If you zoom in further, you find that there are crystals everywhere you look. If you look at this wall, you'll find that it looks like that, loads of little crystals. If you look at the steel or the aluminum of this laptop, you'll find it's full of crystals, billions of crystals. And our ancestors had never seen those crystals until the microscopes were fairly advanced, but they knew they were there. If you go to the basement of the material science department, you'll find the forging labs. And if you have a go at forging, you'll discover what our ancestors knew a long time ago, that in your hands, when you hit a piece of metal, you can tell what stage the crystallization has happened. You can tell fine crystal structure, you can tell annealed structure, and that the ability in your hand to feel that was known. I mean, this is how we progressed so far without this map, because people could feel it in their hands. And this is the whole gig, of course, about putting things in the fire and hitting them, is you're not just shaping them, you're changing the crystal structure. Why would you want to change the crystal structure? Because it turns out, just like with the living side of the world, that if you change something at this scale, you change its strength, its toughness, its fracture, everything at this scale. And they knew that. But, of course, they sort of struggled with understanding that sometimes steel was good and sometimes it was bad, sometimes bronzes were good. What was that about? And that will turn out to be down here at the atomic scale. If we go down further, this is a single crystal, the most important single crystal probably of the 20th century, although there's a few that would rival that. But this is a single crystal of silicon. And, of course, you put 1 billion of those together and you have a silicon chip, and that's the internet revolution. That there, it's something that's the size of a thumbnail inside every one of your phones and laptops. And these are thinking pieces of material with no moving parts. But they can do things much faster than we can in our head. And so this is quite an amazing kind of achievement, right? Zoom in further and you get to the nanoscale. And here things self-assemble, right? All you have to do is create the right conditions, and you get a buckyball, or you get a nanotube, or you get some other vesicle. So this starts to kind of make sense of this thing about the machines inside the cells, the same sort of scale. These things make themselves. Why? Well, because we live in a universe where that happens is the best explanation, right? The quantum mechanics operating, the scales operating, the environment inside a cell is what allows that to self-assemble and operate as a machine. We can't do that yet. We can make this stuff, we can observe it, but we cannot make things from nanostructures that really operate in anything like the sophistication that nature can. But we will do that. I'm convinced of that. And in fact, I would go further. I think that one of the big achievements of the 21st century will be to cross this divide, that actually the inanimate world will become animate, that will be what we do this century. And I'm going to try and lay out a few reasons why I think that's going to happen. But before I do that, just to sort of say, yeah, of course, at the bottom here, we know there are atoms. There's roughly 100 types of different atom. And of course, the thing that we discovered is that it's the things at the bottom are not the most important things. So it's not about reductionism. Material science is the opposite. Material science is a synthesis subject. It's a creative subject. You can change the atoms all you like down here. If you haven't got the right microstructure, the thing's going to fall apart. If you haven't got the right mesostructure, the thing's not going to work. So you have to make sure that all the different structures you want all fit together, all work together to get you to the moon or to Mars or to call your mum. That's the truth. And so it's about putting all the different parts together. It's an incredibly creative subject, but it's also a incredibly complex subject. And that's why it's taken us so long to get this map. But now we have it, and we bequeath it to you. I mean, I say we. I mean, I loved being part of the gang who can take credit for this. I've obviously done tiny amount, and all of us have in reality. But it is an amazing human achievement, this map. It is like giving people the map of the globe. It is exactly as powerful as that. And you can navigate it and take it where you want. You can take it and you can create a conscious robot, maybe. Or you can get to Mars. Or you can heal someone who's injured or needs a new leg. Or you can do anything. This is real power. So what will we do? So I thought I'd kind of sketch out a few problems that need to be solved in the next few decades and what material science is doing and how I think we should, as a community, approach these problems. So energy is obviously one. So we've got to wean ourselves off oil and the hydrocarbons because their burning is contributing to global warming, and that's going to get really bad. Global sea levels are rising. That's particularly concerning for the east coast of America, amongst other places. And if you don't want in 100 years' time to have incredibly bad storms here that wipe out huge numbers of people and completely desalinate all the water, or salinate all the water, then we've got to do something. So the first thing we've got to do, and it's probably not the only thing, is to wean ourselves off fossil fuels. But we have, in a way, got a material science technology that will already take us quite along the way there, and it's called solar cells. So why do we need to do anything more? Well, two things. One is these are very expensive, roughly, and they can't really compete yet with the cheapness of oil. But two, I don't think any of us want to live in a country that is almost completely covered with these. And that's really what has been the kind of de facto solution. Let's harness energy from the sun. Great, let's have a whole field of these things. Really? Really? Is that where we're heading? I mean, apart from just the obvious fact that you don't really want to do this and just and knock off crops from the world, because actually food shortages is also going to be a big problem. So, how to do it? So what would you do as a material scientist faced with this problem? Well, we are faced with this problem, so let's think it through. Well, it's a multi-scale problem, in my view. You obviously, you want to harvest the energy from where you use it. So you probably want to harvest it from buildings and from the urban environment. But if what you do is bolt it onto roofs, you again potentially have this problem, which is that A, it's kind of a clunky solution. B, it's not going to work everywhere. This is a picture, by the way, of, you can't really see it very well, of solar cells all around the outside of a building. You change architecture. You kind of make everything black. It's not a very attractive solution. So although we're getting very good, and the other thing, of course, it's very expensive. So people are approaching this in different ways, and there's lots of work going on here at MIT. It's one of the most innovative places in the world for this. Quantum dots and perovskites, which are sort of cheaper versions of the silicon solar cells I showed there. These optical guides to take more advantage of the light hitting the building, quantum dots. So we've got lots of things in our armory at different scales that can help us harvest light in different ways and turn it into electricity. But what we don't do very well at the moment is that these people tend to work on their own in labs, optimizing devices, and the people up here, bolting things to buildings, don't talk to these people, roughly. And the people building buildings, enormous skyscrapers, don't talk to anyone, as far as I can work out, right? Now, we have to work out a way of building material, building skyscrapers and buildings in which all of these scales are aligned. We have to. It's like it's the obvious thing to do. The built environment should be integrated, just like your phone is integrated. It's just a bigger problem to solve, but we're totally up for it. But I think it's about merging concrete, steel, and glass technology with harvesting energy from the sun. And it's got to work at all scales. It's got to be both efficient, but it's also got to be beautiful. It's also got to be a place we want to live, right? We don't want to kind of live in a world just full of fields and fields of solar cells or roofs plastered with them. So that's one thing. The next thing, of course, is that what you're going to do when you're storing all that energy up. Well, you've got to put it in a battery or some sort of storage thing. At the moment, batteries are kind of stuck. They're stuck in quite a good place. Lithium batteries are pretty amazing. And they've taken us as, to having laptops and phones and to having electric cars that will probably do the job. I think everyone kind of recognizes that lithium will take us into an economy that we could compete with fossil fuel cars, just about, but it's not ideal. At the moment, the way we make them is we're very sophisticated down here, cathodes, anodes, graphene, graphite. We can have lithium ions intercalating. So this stuff we're good at, and we've made it dense and lighter. But up here, as you get to the bigger stuff, we just put it in a big block, or we just we works for one thing, we'll just make a whole load of them. I mean, the Tesla approach, I'm not criticizing it particularly. I think they're doing a really good job of sort of making electric cars affordable, but it's just literally make bigger batteries and cheaper batteries. But I think we can do better than that. I mean, if you look at your muscles, you have distributed energy sources and storage in your body. Why don't we do that? Why don't we think about distributing storage throughout the body of a car, throughout the body of an airplane? Why aren't we kind of trying those out? And I think part of the reason we're not doing that is because, again, we're good at doing stuff at the micro and nano scale, and we're good at making big stuff, but we're not good at linking those two together into a manufacturing system. So I think a lot of the problems we've got coming, to solve them, we've got to be more multi-scale. And this is no truer than when you see carbon technology. So carbon technologies come along as a result of trying to make aerospace more efficient. So now we used to make airplanes out of aluminium, and now we make them out of carbon fiber composites. And so this stuff, and Tesla and the electric cars are lightweight for the same reasons, strength per weight ratio. So basically you're trying to use energy more efficiently by having anything you move be very lightweight, but still be stiff and strong. And carbon fiber composites are it. But it's a fabric. That's what it looks like. You infuse a plastic into it, an epoxy, and you make this amazing material, which it looks like this under the microscope. And actually, if you look at that carbon, you find that most of it's amorphous. And that means that the strength of that stuff is mediocre, actually. Even though this is quite an amazing material, it can easily beat all the metals. We have much better materials. They're called graphene, 2010 Nobel Prize, nanotubes. These have much superior properties to the fibers, the amorphous fibers being used in your airplanes and the Tesla cars. But no one yet seems to be able to make anything out of this stuff and put it into a big object and actually get those factors of 10. Because imagine getting a factor of 10 in weight. I mean, according to the properties, that is doable. In fact, better than a factor of 10. But no one can do it yet. But if you can do it, you increase by a factor of 10 the range of that car. So what's at stake is very high, and yet what has to happen is that we have to work out the microstructure and the macrostructure and the manufacturing system. So it's there for the taking to make a huge impact, and I think it has to happen. And if you want to see another kind of technology that relies on carbon fiber and just how massive it is. So wind power, these things are carbon fiber blades. They're the size of jumbo jets, each blade. They're just these enormous pieces of tech, and we're going to rely on these as well, wind technology and wind energy. And getting this stuff to be stronger, lighter, and therefore bigger promises to have an enormous impact on our ability to harness energy from the wind. But of course, I couldn't mention energy without mentioning fusion, this is the answer, of course, right? MIT told us last week that it was, so it must be right. Within 15 years, I think, all of that stuff I talked about, solar cells and wind power, is going to be irrelevant, because this is going to be on the grid. Or not. And the or not comes from the material science community, who go, whoa, wait a minute, you might be able to get a plasma that gives out more energy than puts in 15 years, but that plasma is going to output neutrons with 14 mega electron volts coming out, and they will destroy any power station you build around it at the moment. We have no building materials to build a fusion reactor that will not be destroyed by a plasma that works. So actually, the problem is more than one thing. It's more than just making the plasma give out more energy than put in. It's actually building a robust engineering system that's safe, and we just have no idea how to do it at the moment. And if you think about what happened to fission, what happened was that we ran headlong into fission, sort of in love with it in the 1950s, and there were actually, then they had to retrofit all the science later as these things started to fall apart, and they hadn't realized that essentially when you get neutrons into metals, you get massive vacancies, you get hydrogen, helium inside the structure. It causes all sorts of mechanical properties. You get embrittlement, and you get enormous dangers. So fusion, for fusion to work, and I'm the one I want it to work, we need an enormous amount of material science to be done to get a structure that will not fall apart. Okay, so that's energy. We'll sort it out, I'm pretty sure. The talent in this room, no problem. Another problem we've got is that pretty much the whole momentum of materials and manufacturing and the material, all of this stuff around us has been about making new stuff. We love it. It is essentially who we are. Like, who doesn't go to the shops and just think, you know what? I need a new T-shirt or a new pair of shoes or a new phone or a new it's very hard to resist, right? We like new stuff. We make new stuff. We're good at making new stuff. What we're really bad at is unmaking it. In fact, we've given almost zero thought to that. And actually, because we're so good at making stuff, it's actually getting kind of in the way. Like the stuff we want to throw away, we don't know what to do with anymore because we didn't really think about unmaking it, and we haven't thought about unmaking it. So let me just give you a few examples. This is the periodic table. The elements that are highlighted are in a compact fluorescent light. And these are the lights that you see around. This is the most efficient way to turn electricity into light. Now, that's quite a lot of elements: sodium, magnesium, calcium, strontium, barium, yttrium, chromium. I won't boast into song. But you'll notice that some of them are orange. Now, these are orange ones because they're quite hard to get hold of, or they're very valuable in terms strategically. i.e., tungsten is a strategically restricted material in the US. Because it's so important for manufacturing, and especially for your military, it's a restricted material. But actually, it's in a light bulb, and guess what? It gets thrown in the bin, and it's never recovered. That's kind of crazy. So is the mercury. The mercury just gets released into the air and poisons people. Now, why did we do that? Why did we make something that was so complex in terms of its material characteristics just to turn electricity into light? We had a much simpler version before. And the reason we did it was before we had incandescent bulbs, and they were very inefficient. They were 90% inefficient. And this is 90% efficient. 90% of the energy goes into light. Hooray. But we never thought through what we would do at the end of their lives. So it all just goes into a landfill, or in the case of mercury, into the air. If you've got a smartphone, well, you have more than half the periodic table in your pocket, which is an amazing achievement. And in some ways, we should just be proud. If you ever end up going down a time wormhole and go back to the 17th or 15th or 12th century, you can just whip out your smartphone and go, don't worry, it may not work in this time zone, but I have all the elements here that we need to rebuild civilization and get me back home. So you will be hailed as a genius, and rightly so probably. But yes, average life of a smartphone, anyone? About 18 months before the call comes. You know the call I'm talking about, don't you? Hello? Yes. I'm due an upgrade? What? Is that true? Really? It's a slight increase in your, okay, but it's new. Why not? You're right, I do need a new phone. No, sometimes those phones do get handed on to family members and so on, but in the end, the phone ends up in a liquidizer at the end of its life and gets made into powder. And then that powder gets thrown in the bin, which is kind of weird, isn't it? And except for the gold is extracted because there is 300 times more gold in that powder. In a kilo of smartphones, there's 300 times more gold than a kilo of gold ore, the most rarefied gold ore you can find. So the gold is extracted, but the rest of them are not economically viable to extract, so they're left there in the dirt. Now, that makes absolutely no sense, and it's not sustainable. And if you've been to any of these mines, you'll know what I mean. Like, mines are just one of those things that we haven't quite managed in general, not every mine, but in general. Mines are environmentally extremely damaging in many, many ways. And this kind of wanton profligacy is just crazy. But it's just a symptom of the fact that we're very good at making things now, magic things, but we're very, very bad at unmaking them. And the kind of epitome of this is this situation with plastic, which we make by the 100 million tons, and we love, and as I said before, is the source of so much joy in our lives, the origin of cinema and photography and sneakers and shoes and running shoes and all sorts of great things. A good night's sleep being one of them on your foam mattress, but memory foam. But the problem is that people, when it's in the form of a kind of disposable, one-use only plastic, people throw it away. It doesn't seem to have much value. And there's so much of it ending up in the sea now that by 2050, if it continues, there'll be more plastic in the ocean than fish by weight, which is a lot of plastic. Then you think, well, come on, this is now he's exaggerating. This is solvable. This doesn't need any sophisticated multi-dimensional, what is he talking about thing? Okay, but I beg to differ. So here is what one of just a normal kind of milk bottle looks like under the microscope, and it's made of polyethylene, high density polyethylene. Ethylene is a little molecule that looks like that. If you polymerize it and make a plastic, it looks like that. If it's a line like that, it's crystalline, and that gives the polymer a bit of strength. And if it's randomly structured, it gives it some toughness. And actually what the manufacturers want is a combination of both. And that's what you see here. And that gives that very thin bottle an enormous amount of strength and toughness, low density, so that if that was a glass bottle and you dropped it, well, we know what would happen, right? Milk everywhere and would smell terrible, like cheesy for weeks, right? In the back of the car, no one wants that. But this amazing material, high-density polyethylene, will resist that fracture, mostly. I mean, occasionally it won't, but it mostly will. And it'd be 10 times lighter. And it's a wonder material. Why wouldn't we use this? We do use this a lot. It's the argument used for all of these things. Your bleach, your hair, your shampoo, your soaps, all of the stuff is better off in plastic. It's chemically inert. It's lightweight. It's totally recyclable. It is totally recyclable. It goes back. You can make it into little chains. And the problem is that that little cap at the top there, can you see that cap, is green. Now, that's also made of polyethylene, but it's got a dye in it. And that dye gets back when you recycle it into here. And then it's really hard to get out, and it makes the whole plastic look a little bit off-white, and no one wants to make a milk bottle out of it anymore. And so it's valueless, almost valueless, to the recycler. They would much rather pump some more oil out of the ground and make new plastic, and that's what they do. So it has almost zero value, and so it ends up in the sea. So what we did is we made something that was recyclable, but the design, putting dyes in it and many other kind of multi-materials, when you put a foil in it, when you put a plastic foil that's non-recyclable, when you mix them all together, polymers hate it. You lose your properties. And why do you lose your properties? Because you're messing with the microstructure. And that's what we know from material science is something you don't want to do. So control of the microstructure has to be part of recycling, but it's exactly not what's part of any recycling method and any design method. You look at any products and look at the multi-materials in there, and you know it's never going to be recycled. So we're dumb. We're dumb at unmaking things because we don't design them to be unmade, really. That's the problem. So how can we change this? Here's my best guess at how I think it could go. So this is something called the circular economy. And this is what we currently do. We take stuff out of the ground, We make stuff, we're brilliant at it, it's fantastic, we love it, we get bored of it, it goes in the ground. That's what we currently do with pretty much everything. Obviously, if it's a car, we repair it for a bit, maybe for 10 years. If it's a washing machine, we repair it for 7 years. If it's a laptop, we repair it for 3 or 4 years. And if it's a phone, this cycle is quite short. And it's getting shorter, by the way. And that's obviously a pressure of economics. It is, isn't it? Like, as it gets harder and harder to make a buck, the manufacturers do not want things to last long. Why would they want that? They need you to make it. And this is a fact. You only look up the stats on washing machines. You're always going to need a washing machine in your life. You always are, right? So why not buy one that's going to last you 50, 60 years? It's easy to make one. There's only 3 things that break in a washing machine. And they're easily replaceable. But that's not your attitude, is it? And it's not the manufacturer's attitude. The steel casing around it will outlive you by many centuries. But when you get rid of the washing machine, you get rid of that, for a start, and the drum, the stainless steel drum. Amazing material. Again, you're getting rid of that. The only thing you have to replace are the electronics, the bearings, and somehow the door locking mechanism. Anyway, you know what I mean? But essentially, that is not the paradigm of economics that we're in, or manufacturing that we're in. So what I'm talking about in terms of repair and repairability is actually about society. It's about the whole economic system. And that's always been true of materials. It is not locked up in just solving technical problems. Because it is multi-scale, because it reaches all the way through to you, the size of you, and the size of the roads and the cities. It is the city, right? It is the country. It is the satellite system. So this thing couldn't be bigger. Our material world couldn't be bigger. And so, of course, it involves politics, and of course, it involves economics. And that's why, as a material scientist, you have to also operate in those arenas. You have to understand the cultural value, the economic value, the political value of all these things. And I think to move to a system where things are designed to be repaired, that light bulbs, just a little light bulb, is designed actually to be circular, for all the ingredients of a light bulb to go back around the cycle. So you're no longer digging stuff out of the ground. You're no longer doing this. This is totally doable from an engineering point of view. The hard bit, the really hard bit, will be the economics. But I think it's something we all need to do, because otherwise we are going to ruin the world. Okay, then the next thing I wanted to talk about was this thing I postulated at the beginning, kind of grandiosely. We're going to make animate materials. But I believe it, and I'm working on it too. So there we are. At least I'm putting my mouth where my... No, anyway. So what does that mean, animate materials? Well, they exist already of sorts. This is something called self-healing concrete. And the logic makes perfect sense. You've got this enormous body of water. You're building a bridge across it. It costs a lot of money to do that. It costs a lot of materials to do that. It costs a lot of energy to do that. Then an enormous storm comes along, and it kind of injures one of the pillars in the middle there. You have to get people out there. You have to close the whole bridge. It's cost you millions of economic growth, pollution. This is not what we want. We want that pillar to heal itself, just like a damaged branch of a tree would heal itself. Is that so hard? Well, no, it doesn't. It turns out to be okay. So what self-healing concrete does as an answer to that is it's normal concrete with normal refill bars, but it's got little bacteria inside it. And these are bacteria that can withstand high alkaline conditions, conditions you find inside concrete. And they'll stay dormant inside this concrete, totally viable as organisms, for 50 years. But if a crack opens up as a result of, let's say, of that storm, and you get a crack here, the bacteria smell, damp air. They wake up, yawn. They look around for food. The concrete manufacturers leave little packets of starch inside inside the concrete. The bacteria eat the starch. Delicious. They then have a poo, which is calcite. Here it is. And it's one of the major constituents of concrete. They then eat some more. They then exponentially increase, as bacteria are wont to do. And they eat, they poo, they eat, they poo, they eat, they poo, until they hit the edge of the crack, leaving pristine material behind them. And then they die, unfortunately. I know. It was a great story, and then tragedy. But I'm sorry about that. This is a prototype material. I mean, you can buy it. You can make buildings out of it. You get 90% of the strength back, but it's cruel to bacteria. And I think it tells you what we could do, and also it tells you also that it doesn't need to be these synthetic animate materials or nature. Actually, probably the starting point will be some combination of both. I don't think it's impossible that mobile phones of the future will have bacteria in them that do something. I think that's perfectly possible. So it's that interrelation with those two systems, I think, is coming. And this is a good example of it. Stuff that I'm working on is self-healing roads. Roads are boring de facto until they're not working anymore, and then they're infuriating. It's hard to feel affectionate to a road, I know. But if you study roads, which I have been doing for the last couple of years, they really are, I'm going to try and persuade you they're fascinating. Okay, so how are they made? They're made from aggregate. Here it is, you can see it, mostly, 90%, 95%, so that's stones. And then in between them, they're glued together by a mastic, so-called, of this thing called tar or asphalt. And under the microscope, you see different phases of it. And there's a matrix phase called a maltine phase and another phase called asphaltene. And of course, if you think where tar comes from, this is old organisms that died. So loads of hydrocarbons and intricate mechanisms that I was pointing out earlier. All the machines that make you alive, this is what oil is. All these bits of them. So are you so surprised that in tar, here they are self-assembling, I kid you not, into my cells inside the material? They do. It's like burying Lego and then getting it out again later and being surprised that you can kind of make a replica of the Starship Enterprise. It's like it still works. But we use it for roads now. And so it turns out that this tar at about 20 degrees is a liquid. And so even though the road seems perfectly solid, actually the mastic and the glue and these little phases, they're constantly wriggling around and moving, and there are little small molecules in there creating spaces. And so if a lorry comes and makes a little crack inside there, the liquid just reflows into it over a couple of days and heals that crack. So this already happens. And it's a self-assembling system. But of course, you'll have noticed that roads don't last forever and potholes do form. So what's happening there? Well, on days like today, in fact, months like this month, the temperature's too cold for that to happen, right? So the cracks open up and they aren't refilled, and they get bigger. Water gets into them. You get freeze-thaw cycle. They get bigger and bigger. The aggregate is extracted, and there's a point of no return where you get runaway. You get a runaway building to this. So if you think about it, summer, winter, summer, winter. The summer is healing, the winter is damaged. The summer is healing, the winter is damaged. But at some point, you get these kind of cancerous moments where the potholes just become runaway size. Now, how to deal with that? Well, actually, as a material scientist, you can think of many different ways of solving that problem. One of which is that when you analyze why you get this runaway moment, it's because actually you get oxidation of the mastic here at the high scales at the surface. You see the tar going grayer and grayer. That's an oxidation. And so the liquid becomes higher and higher viscosity. So why not replace its former youth? Why not give it some chemical ingredients that will make it more liquid? Makes sense, right? So quite a lot of people have been putting little capsules of sunflower oil into the road, and also little slivers of steel. And what happens is that the crack opens up, it splits one of these capsules up, and then that gives it some ingredients to make it more liquid, and then it heals the crack again. And that works in the lab, amazingly. With the little slivers of steel, they've created a road with this stuff in. It's a motorway in Netherlands. And they've made autonomous vehicles that drive up and down this road, and they create an alternate magnetic field, which basically heats up the iron, and it makes the temperature higher in the winter, and so heals the cracks. So those are two possible ways of doing it. And there's lots of different technology. Our method is actually to be part of a bigger system where we're trying to work out how to 3D print into the holes once they're bigger using drones. So 3D print So we have a sort of like insects. They want to find they want to find these holes. So they tour the whole road network, constantly looking for holes, and they sit in them, and then Anyway, we've got a working prototype. I'll show it to you another time. Anyway, so 3D printing of different materials has been this big, amazing revolution in material science because it's a different way of making things, it's a different way of repairing things. Where will that take us in terms of kind of animate materials? Well, actually, it's not just in something like this. It's obviously the applications in the human body are even bigger because the thing about bodies is that you're all different. You all have different sizes of this, that, and the other. So if you want to have a replacement part, it's always going to be your size. It's not going to be a standard size. It's not going to be small, medium, large like your shoes, right? So in fact, what 3D printing does brilliantly is that I can MRI scan your jaw, as this woman's jaw was scanned who had cancer, can get the exact shape of her jaw, and then print it out. And that's what happens to this woman. And then that's replaced, and then she no longer is going to die of cancer. And it exactly fits her. So this is economically viable in a hospital environment because of the efficiencies of digital scanning going to manufacture. You haven't got to do a whole lot of prototyping in the meantime. But you'll notice that actually there are holes here, and they look a bit odd. And that's because this is titanium. And titanium is one of the few metals that is biocompatible, i.e. it's not going to cause infection and rejection from the body. But it's the wrong density. It doesn't match bone density. So they've tried to match the jaw weight by just cutting holes into it. That's a bit clumsy, isn't it? Wouldn't you rather 3D print cells and bone and tissue? Well, of course, people are doing this all over the place, including a lot of people at MIT. And this is sort of going, we're at this point where people don't really know how far this could go. Obviously, the idea of being able to 3D print a liver, a kidney, a heart valve, this feels like something we'd want, right? Because there aren't people who die by being on the waiting list for those organs and looking for donors, and complications. Probably in your life, you'll all know someone or be someone who needs this. But it turns out that cells don't like being printed, generally. They die often because of the shear forces. And actually, one of the best ways of doing it is actually to 3D print something called a scaffold, which is the shape you want it to be, but isn't the material. So so you zoom in, and what you have is these tiny fibrils. These are polymers in this case, and these purple things are the cells, and you infiltrate it with the cells of the patient. And it turns out that then you have this sort of hollow scaffold of the object. It could be a nose, an ear. At the moment, these are the things that mostly seem to work in terms of implants. And the cells grow. They create the tissue, your tissue. It turns out that if you want a particular tissue type, you have to control not just the chemistry of these fibrils, but also the shape of these holes, because they're responding to mechanical forces. And actually, they're feeling their environment, the cells. They don't see, they feel. And in fact, this is the most, this is February 2018. So this is a clinical trial of, I can't remember how many patients it was, but maybe about 20 or 30 patients who had deformed ears, and they had 3D printed cartilage implanted in them, and you can see pre-op, post-op, and then you can see over the number of months how normal tissue grows from their stem cells, and then that's the end result. So that's where we are in February 2018. The ear is not plumbed into the body in the same way your liver or kidney are. It's not doing something like a heart. It's not beating, but there are people in MIT and other places who are, making great strides in this way. And I think really it's going to be really interesting to see whether this kind of technology, 3D printing plus scaffolds, will make the whole of the health industry completely revolutionized by allowing us to have essentially body parts made to order for us. Okay, I've got two more things to say. I'm slightly running. One more thing to say. Two more things to say. One more thing to say. Okay. Food and drink is something that you might think, oh, well, that's got nothing to do with material science. But, it's edible materials, is the way I look at it. And delicious edible materials most of the time. Of course, we need to do something about them because, it turns out that the eating of meat in particular and the land use change, and if you look at the increase in population, then what's going to happen is that actually the contribution to CO2 and global warming of meat eating plus the land use change is going to make a huge difference. But I'm willing to bet, actually, how many people in this room are vegetarians? Quite a minority. Let's say 10%. Is that fair? 10% of people are vegetarians. The rest of us eat meat, right? Now, I'm pretty sure we don't require an animal to be killed for us to find meat delicious. Like, it's not the death of the animal that is so delicious, right? It's not. Maybe for one or two of you. But mostly it's like, that's a kind of slightly guilty secret we have and we feel bad about it. It's just that bacon sandwiches taste so good that we can't resist them, roughly, and beef and all the other things. And we sort of, if you could make me a bacon sandwich as delicious as bacon, but didn't involve an animal killing, I'm fine with that, right? We're all fine with that. So that surely is a very well-posed problem. How to make something as delicious. It's just like saying, I want something that's strong and light and tough. But this is like saying, I want something that's delicious, right? But doesn't involve an animal dying. You know? That's a material science problem right there, because it's the multi-scale. It involves molecules, involves fat and protein and carbohydrate being layered. It involves texture, which is a microscale problem. It involves all these different things. And if you think, well, Mark is just sort of being kind of idiotic, this has got nothing to do with material science. I've done some work in this region myself and published a few papers. But I guarantee you, I think material science has got a lot to offer. And I think this is an area you should think about strongly if you're thinking about going to material science. It's a big area. And I think, yeah, and the quest is big, right? It's $1 billion. It's $1 billion industry out there of meat. And it's going to be the next big thing, bigger than Google. Anyway, so finally, to say that, so how do we discover all these new materials? I've been talking about how do we do it all. Actually, you know, one of my biggest inspirations is this guy called Cyril Stanley Smith, and he is, he's one of the instrumental people in this department. He started up the archaeology materials. He was a metallurgist who had a joint appointment in the humanities here. And you'd be, if you don't already know his work, you should really look him up, because he's an incredible character. Worked on the atomic bomb. He just spans the arts and sciences. He does everything that I've been talking about, being able to understand different scales, the arts and the sciences. And yeah, what an inspiration. And I think that is essentially where we need to do. 21st century materials development, we've got the map, right? We know the map. This isn't going to change, right? We're going to get more details at every scale. But this essentially is there it is. It's like there's not going to find a new continent on the Earth. We know which continent's on the Earth. We know where everything is. But what are we going to do with it? And that is the hard bit. And I think basically, like as Cyril Stanley Smith was rightly pointing out right at the beginning, that actually materials are the heart of any university, the heart of any society. They involve chemistry and physics, they involve architecture, they involve gardening, they involve chefs and biologists, as I hope I've pointed out. They involve miners and economics. They involve it all. It's a really incredible challenge, and it's an amazing place, but they are at the epicenter of everything. And that is where I think you should be if you're going to study material science. So with that, I won't go on any further. Just to say that, as mentioned before, I have written a lot of this down in a book called Stuff Matters. And if you don't get a chance to ask me a question today, do tweet me and I will get back to you. But thanks for listening. And
Thank you for that wonderful bird's eye view of our field and how heroic it is. In light of the late hour, I think I'd like to keep this to just maybe one or two quick questions, and I will favor undergraduates. So if you're an undergraduate with a question, raise your hand now.
Oh, there's one.
All right, please.
Yeah, sorry.
So you're talking about how what is really necessary in a lot of industries, such as energy, is the collaboration across scales. How do we foster that collaboration between the scientists in the labs and industry and construction?
Yeah. How do we do it? Oh, yeah, sorry. Okay, thank you for that, because actually it allows me to go back to a slide I skipped. Brilliant. So this is how we do it. And I already talked to talk to your faculty here, and I think it's pretty much the same as how you're doing it here, is that actually what you need to do is make sure right from the beginning of any project, so solar cell development, you don't want to do solar cell development without involving the architects, all the humanities people, all the psychologists, all the designers. You've got to get them all in right at the beginning. Right at the beginning. And it might seem like they've got nothing to add to this quantum mechanics thing, but they do. I promised you they do. Because they will count, it's like the fusion thing. They'll go, hold on a minute, if we go down that route, this thing is going to be lethal. This thing, the risks go massive. And you go, yeah, but maybe not. And you go, no, you have to take those things seriously now. And I think that's what those humanities people do really well. It's what artists do really well. They are very good at looking at complex systems. They're really excellent. And they're very, very smart. But of course, so it's getting the team together early on. I think what we've done badly in the past is we think we'll have to get it to the point where it's almost commercial before we involve these people, the politicians. And that is too late for a technology. It usually then there's all sorts of agendas pushing it forward, and it will happen anyway. But maybe be a disaster, maybe not, but often is. So that's my answer.
That's a great question. We have time for one more, and I'll broaden it up. I won't require ID for the next question, so... Does anyone else have a question for our speaker? All right. Well, I suspect you probably do. And so if you're not willing to air the question now, I would invite you to stay with us after we adjourn here. Right outside, there will be a whole bunch of food, courtesy of DMSE, the Department of Materials Science and Engineering. We also have some paraphernalia by the door that sort of tells you more about our department and our curriculum and what we care about and what we love. And you're invited to stay around, enjoy the food, enjoy the discussion with the faculty and students of our department, and also with our guest speaker, for whom I would like to request another hearty round of applause.